Miss Jody here with the last video of STEAM for this year. Bet you're glad to hear that. Finally finishing up. Took a little longer doing it this way with our online classes, but at least we are finishing up. So we had 2 more chapters to go from the last video. If you remember, we were finishing up lenses and instruments. The next chapter, chapter 22 in basic physics, was all about light as a wave. And we already talked a lot about light as a wave. And so in that chapter, I didn't feel like there was a lot that was interesting enough to do in a whole section on, especially since we're kind of running low on time here. So I thought the only thing that's really major in that chapter is just understanding polarization. And so I thought I would send you a diagram along with today's diagram on color, and it would in a video on polarization of light, and we can fit that, just add that into our lenses and instruments, because there are lots of instruments that polarize light. So I will do that on the second half of the diagram, because there's only one diagram today for color, which is this diagram. So on the other half of it, I have the polarization one, and like I said, I'll send the videos, and then that way you can just do that diagram, and we don't have to do a whole chapter for chapter 22. So I'm taking that one out, and we discussed already the double slit diffraction experiment. We already talked all about how light as a wave, light as a particle. We spent a lot of time on that, and even the chapter in Exploring the World of Physics on light, we had already discussed all of that also when we were studying light. So instead of hashing all that up, I skipped ahead to chapter 23, the last chapter of the book, on color. And I thought this would be a fun one to finish up our studies on light anyway. It's fun to take a look at the world of color. Okay, so what is color? First of all, visible light. That's where we're going to be seeing the color spectrum. And so we have to understand what visible light is, and we all know this pretty well, the electromagnetic waves that the human eye can perceive. So of the spectrum, the 7 main categories, with the radio waves, microwaves, infrared, right smack in the middle, visible light, that's what we talk about today, and then of course ultraviolet, X-ray, and gamma. So this little right smack in the middle guy is a range of frequency between 400 terahertz to 800 terahertz. Now this is rounded, obviously, because red actually starts at 389, but just to kind of round it up. Wavelengths would be the length of the wave, obviously red being all the way at this end, the longer wavelengths, 770 nanometers all the way to 390 nanometers. Okay, so as you can see, here is the relationship. You have, when you are lower frequency of light like red, you have a lower frequency. Remember, we talked about what frequency is. It's how frequent it is coming at you or whatnot after or passing a certain point. So only 400 terahertz versus all the way on the other end of the spectrum, which of visible light is going to be all the way up into the 800. So it increases. It increases in frequency, but it decreases in wavelength, because wavelength is how the length of the wave. And if I was going to try to draw it, which would be obviously not very what's the word to scale or realistic, but if I said red, I'd be like a longer wavelength, and then it gets smaller wavelengths, and they start to get smaller. This is really terrible, but you get my point. This is me trying to, this is really bad, but you get it, okay? So the wavelength is going to decrease. So your frequency will increase and your wavelength will decrease. Now, of the visible spectrum, we have the lettering, Roy G. Biv, that you've heard before: red, orange, yellow, green, blue, indigo, and violet. And of course, there really isn't such a thing as indigo, but if you remember any of the back in the day studies, I can't remember who it was that added indigo. Might have been Sir Isaac Newton. I'm going to have to look that up, but one of the gentlemen that was working with the colors, no, I don't think it'd be Newton, but one of them added indigo because they wanted the 7. 1, 2, 3, 4, 5, 6, 7. They were locked on that 7, and of course there's 7 categories in the regular spectrum, the electromagnetic spectrum, and then 7 being God's number. It said that was distinguished there to add that indigo into the spectrum. But really, it's indigo and violet is 1. And you can see that by the wavelength and the frequency categories. All right, so I did the, see, I wrote this sideways, so it doesn't look right. Let me not write this sideways here. So let's do frequency and then wavelength here. So I just wrote out the spectra. That way we could use it for reference. And so you note, so red would be 389 to 476 terahertz. And then see, I drew the line, 476 goes up to 476. So see, it's a category. And what it talks about, I don't remember if it's in this book or maybe another book, but many times people don't realize that this is a whole category for that particular light frequency. And so you could be at 490, 490, and you get a little bit of a different, they say it's arbitrary. It's like uncertain values. When you say orange, you're talking about a whole bunch of possibilities of orange, or yellow, a whole however much that is about. Well, that one's pretty small, but yeah, I guess they're all not too big there, but a category with lots of different uncertain values. So it's not like green is just 535 in its frequency. It's 535 to 612. Okay, so we have this written out for reference point. The next thing to note is the perception of color is not a property of light. And so when we think of light, you think of, okay, oh, this is green light. There's nothing really green about 535 to 612 terahertz of frequency. So this light, this particular frequency of light and this particular wavelength of light, there's nothing green about it, other than that particular frequency will be bounced off of certain things and come back to your eye, and you will perceive it as green. And so really the perception of light is not an actual the perception of color is not actually a property of light itself. So that wavelength is not really green. It's just how our eyes perceive that. Then there's the idea of the white and black world. So white, all of the frequencies of light entering the eye, giving us that white, and we'll look at the additive and subtractive colors to understand the combinations of wavelengths and frequencies coming into our eye. And then black, no frequencies of light are entering your eye, because instead of being reflected back, they're being absorbed by the substance. Okay, so when something's black, it's absorbing all the light colors. When something's white, it's reflecting back those colors. And it doesn't actually have to be reflecting back, for white, it doesn't have to be reflecting back all, because when you look at the additive colors, if you have the red, the green, and the blue, then you can have that reflected back, can be creating that illusion of white too. All right, but just as a basis for white and black, this is how you learn it when you're younger. And then apparent color of some objects is due to reflecting more than one frequency. And what that means is when you're younger, and someone says, why is this green? The teacher always says, well, it absorbs the other colors or whatnot, but it reflects back the frequency somewhere in here of green to your eye. That frequency doesn't get absorbed and it comes back to your eye, and so you perceive that. But that's just a way of simplifying it, because sometimes it is particularly that frequency or wavelength, but sometimes it's because it's more than one of frequencies that are bouncing off the object, because light's coming in and spreading out, or hitting and then reflecting back, and surfaces are not even. So we talked about that before, back when we were talking about reflection and refraction. You remember that? And we showed like the surfaces. I can't remember what chapter that was, with dispersion and all that. Oh yeah, reflection and refraction. Remember we had the specular reflection where it was like perfectly flat, and then you had the diffuse reflection where it was uneven. I'm really this is getting to the end, isn't it? Uneven reflection. So you have all these things coming at you because surfaces aren't always flat. And so if we have all of the if we have a couple different colors reflecting back to us, they can give us the illusion of a color when that's an illusion of, say, like for instance, if you have the red and the green, if so you have a reflection of those two, it can give you the illusion of yellow bouncing back, and maybe it really wasn't that wavelength of yellow. And that's something you don't usually talk about until later because you don't want to confuse the kids. You just say, oh, that's yellow because yellow's bouncing back into your eye, or that's purple because purple's bouncing in there. And that's not really always how it's working. It's more of a mixture because we don't have those, pure lights coming at us and a pure color bouncing right off, and that's all you get from these uneven surfaces. Okay, but it's a roundabout way of thinking about color as a whole, but we have to know that apparent color of some objects is due to reflecting more than one frequency. All right, and then the second part, and this is going to be such a fast video today because it's only just these two. There wasn't much in this chapter anyway, so but I thought it would be nice to still do to get an idea of it. Okay, all right, so then on the diagram that I sent you, it has these two blocks, additive colors and subtractive colors. And so like we were talking about with reflecting the frequencies, there's also the illusion of a certain light can be formed by combining or subtracting light of different colors. I'm going to try this up a little bit here. Okay, so when we talk about colors and whatnot, sometimes you can combine colors and that will give you an illusion of a certain color, or combine light frequencies, I should say, and it'll give you an illusion of a certain color that really isn't there. And or you could subtract light. Now when I say subtract light, I mean by using a pigment to absorb that particular frequency as you're shining light on it. So not like take the light away, but still shine the light and then use a pigment that will absorb some parts of the frequencies to give you a different color. So the illusion of certain light can be formed by combining or subtracting. So if you're going to combine, that's called the additive side of it. If you're going to subtract, it's the subtractive side of things. The additive is all about basically focusing on the lights themselves coming together to create the different illusions of color. The subtractive side is all about pigments, meaning you're still going to be having light shining. You're not going to subtract the actual light itself out, because how are we going to make these colors if we don't have light? We need the light for the colors, but we're going to use pigments to actually absorb some of those colors so that you can get these different subtractive color side. So how that works is in the additive color situation, okay, as an example, yellow. Okay, so yellow is on the spectrum 508 to 535 terahertz. Okay, so that's its frequency. Now for yellow, you can, like I said, have that frequency and get that reflection feel of yellow, but you can mix green light and red light and still get in this area of yellow. And it kind of makes sense because if you look at green, you think green is right at the end of yellow. So green's right at the end of yellow. So 535, you're still yellow. 535, you're green. Okay, so that's the line. So, but green, you're going above yellow. So you're 535 in your frequency to 612. But red is going to be below the yellow. So yellow being 508, below that, that's where red would be. Red would be 389 to 476, right? So if you look at that, you have like higher frequency and a lower frequency could blend you somewhat in the middle, which would be kind of number-wise. This is right at the end and getting higher, and this is a lot lower down here, but yet still close to 508. Okay, and so when you look at that, it makes sense that if we have, something a little bit above this, lower, but not quite up here, we would have somewhere in yellow. So a mix between these two. So if you have you have the green light and the red light and you shine them together, you can get the mix of the yellow. And I'll send you some videos of these experiments where you put the two lights together and you get the yellow. So additive, you've added 2 to get your yellow. Another example would be, obviously, you add these 2 to get magenta, add these 2 to get cyan, okay? Another example would be white. White light is all frequencies, right? So it's all of them, Reggie Biv, all together. But the truth is you could take green, red, and blue and get white. And when you're putting these together, if you think of what is white, it's kind of from, what is my spectra, from 389 all the way up to, what is it, 769. So 389, so here I am with red, so I'm this frequency all the way up to, oh, I'm sorry, violet, 666. So if I get violet is 666, the end of blue is 666. The next one for violet is 666. So if I take red, 389, and then I combine it with red and then green, which would be the next one in the middle. I should have wrote these different. So I should have wrote red, green, and blue, because then you'd see them red lower, green next, blue higher in frequency. I'm pretty much got them all in there, shoved in. So you can take green, red, and blue and create white with the only just 3 of the lights, because all of the frequencies are in there roundabout. All right, and then the subtractive colors. So the subtractive colors, like I said, that's when you use pigment. Then the pigments will help pull out the colors that, or will actually absorb the colors that you don't want, or whatever, to create your cool colors. So magenta pigment. So if you have a pigment of magenta, it absorbs green light. And see, if you look at right here, and so here's magenta, and these are part of magenta, which will be blue and red. And then if you don't have a blue or red, if say you're in a light source, you don't have that, that will become black. But you see how green's over here? So it's because magenta actually absorbs that green, so it doesn't reflect it back. These 2 will be what it reflects. Okay, well, what's part of it, but it can't absorb the green. I'm sorry, I can't reflect because it absorbs green light. Yellow pigment absorbs the blue. So see, yellow is only red and green. It's not the blue, which is what's across from it. So see how magenta across from it was green? That's what absorbs. Yellow across from it is blue. That's what absorbs. It's not part of its circle. It absorbs it. And then cyan absorbs red. So here's cyan, and blue and green are part of it, but across from cyan is its red. That's how you remember which one it absorbs. And it's not part of its circle, so it therefore absorbs it. And then if you put all together, so if you put all of these circles together, it'll absorb all of these lights, creating the black. And so on this end, this is going to be giving you white light, but in your subtractive colors, all of these pigments will absorb. If you put magenta, cyan, and yellow pigments together, they will absorb all the light and you will have black, creating your black. And so it's kind of fascinating trying to figure out these different color situations. And so they give a couple in the book. So they say, suppose a yellow object is in red light. What color is it going to appear? So you have a yellow object, right? And yellow object, and it's going to appear which color? So you have yellow, and this next to the yellow is going to be in the full circle here, will be red. Okay, and then suppose a yellow object is in blue light. So if you're in blue light, do you have, let's see, blue. So here's your yellow, and yellow is involved in the red and the pink, but yellow is not involved at all in the blue, right? I mean the cyan side if it's with green, but it's across from it, okay? And so if it's in blue light, and here's yellow across from it, if it's in this blue light here, then we have black, right? That's what it would be. It would be black. So you would have your yellow object in blue light, which it cannot, then you would have black, because it can only reflect back red or green, because red or green could make it. but it couldn't reflect back any of the blue. So it would be black. Okay, and then suppose a yellow object is in cyan light. Cyan, where you at? Okay, so I got a yellow object in cyan light. Yellow object, cyan light, green, right? So yellow object, cyan light, green. So you'd have green. And let's see, suppose a red object is in magenta light. Wait, yellow object, cyan, green, reflecting. Yeah, yellow object, cyan light, green, middle. Okay, suppose a red object in magenta light. So if I have a red object, where are you at? Red object in magenta light. It's between these two. So once you're between these two and there's nobody in between them, where yellow and green, yellow and cyan had the green in between them. Yellow and cyan had the green there, you know. But this is actually the red light magenta, red light right here. These two are right next to each other with nothing. So this will just be red because it's part of its original. This would be like the 2/3 of that particular, of the three to make the color. So there's nothing in between, so that won't be red. And suppose a red object is in yellow light. Red object in yellow light, they're right next to each other. There's nothing in between. Red object and yellow light, nothing in between. So it would just be red. Okay. Suppose a cyan object is in magenta light. Cyan object, where are you at? Cyan object in magenta light. So see, cyan and magenta. See how there's something in between the two? Blue. Okay, cyan and magenta, something in between, blue. Yep, so this would be reflecting blue light. So it would look blue. So if you suppose a yellow object in a red light, it will look red. If it's in a blue light, it will look black. If it's in a cyan light, it will look green, you see? And so this is how you'd figure out how all these colors will work together to create the optical illusion of the colors that we see across the spectrum. All right, so I'll send you some videos and some experiments to do with some light, or at least to watch them. And then hopefully there'll be something that you can do that you can send me a picture of. I did leave some spots in our journal for some pictures, and I've gotten a few pictures from some of you, and I appreciate that. I'm printing those out. I actually sent those out today, and I'll get those in the journal. But at this point, this will be the last video, so I guess we'll be just talking through the classroom and figuring out when we're going to do our other class projects, and whenever we can maybe get back together. We'll see. Okay, so I miss you guys. I hope you're doing well.